Derivatives number 6 is about how to do different operations with derivatives. So we're going to learn what to do when you have to find the derivative of a sum, a difference, a product, or a quotient. We did a similar thing when we did limits. We also had how to do a limit of a composite function, and we'll do that with derivatives as well, but it's a big, huge deal, and it's going to get its own separate section. So these are the operations that we're going to cover in today's notes. So you have here what all the different rules are. We have our sum and difference rule, and this one is very intuitive. Basically, the sum and difference rule, you're going to do exactly what you want to do. So if you have the sum or the difference of two functions, you just find each derivative separately, and then you just add them together or subtract it. So it's very intuitive with the sum and the difference rule. The other two, however, are not. You'll see the product rule that is listed right here. It is showing that when you do the derivative of a product, it is not the product of the derivatives. And I've got a little example down here to show you that. So if we have a function that we're trying to find the derivative of, and my function here is this 4x squared times 3x minus 2. One way that you can find the derivative of this is you can just distribute that 4x squared through the parentheses. So you could take that 4x squared and multiply through the parentheses, and that's what I'm doing right here. That's the approach I'm using. So I get my polynomial, and then I just power rule it, bring down the power, subtract one from the power, and I get this answer, and it's a totally valid answer. Notice that if I were to find the derivative of each one of those functions separately, so for instance, if I had the 4x squared, and I said, oh, well, that derivative is 8x, and then I take my 3x minus 2, and I say that derivative is 3, I get a totally different answer here than I did over here. And I have here that this one is not the right one. The correct one is over here. And so what we're saying is that the derivative of a product is not the product of the derivatives. So one way that you could do it is exactly as I did in this box over here. It's a totally valid approach, but sometimes multiplying out is not always feasible. So we need to find another way, and that's where the product rule comes in. So let's go back up here and see what it looks like. So when you're doing the derivative, notice this Leibniz notation, the derivative of f times g, it is f times g prime plus g times f prime. So it's one of the functions times the derivative of the other plus the second function times the derivative of the first. So however you can remember this, it's actually a very forgiving formula because multiplication is commutative, so you could switch these guys around. Addition is commutative, so you could switch the terms around. So however you can remember this, there's different varieties, so whatever you like best is how you're gonna recall it. So let's see what this looks like in action. So we already know the answer to that first example because we had done it in the box to the right. But let's see what it would look like with a product rule. So I'm going to treat the 4x squared as my first function, my f of x. So I could call this f of x. And the second function, the 3x minus 2, I will call that g of x. So basically, I'm just going to take the first one as is, write it down, times the derivative of the second. Derivative of 3x minus 2 is just the 3. And I'm going to add the second function as is, 3x minus 2, times the derivative of the first. So where I'm sitting right here at this step is the derivative. The rest of this is just algebra to simplify it. So I'm going to multiply these first two factors together. So that's the 12x squared. Take that 8x and it's going to distribute in from the back. So that's a 24x squared minus 16x. And then I have a pair of like terms here that I'm going to pull together. And you'll see that we get the same answer that we got when we had done it initially over here. Sometimes you can manipulate a function algebraically and not need to use the product rule. However, there are times when you are forced into using it. So even though in number 2, you could multiply the two binomials together and just use a power rule, let's go ahead and practice using the product rule on this one. So in my original problem, this x plus 1 is my first function, and this x squared minus 4 is my second function. So I'm just going to go through the words of the product rule. So it's the first times derivative of the second, plus the second one times derivative of the first. And at this moment, my calculus is done. This is my derivative. All that's left is just to simplify things. So I took this 2x and I distributed it through the parentheses here, and it gave me this. The 1 didn't even do anything over there, so it's just the x squared minus 4 over here. And now I'm just going to combine my like terms. So my 2x squared plus another x squared. And this is my derivative function. It is an expression that tells me what the slope of the tangent line is on any point on this graph of y that I want to pick. On example 3, our only choice is the product rule, and it just operates the same way. So this x squared is my first function, this sine x is my second function. And just recall from derivatives number 5, we had done this from a graphing standpoint, that the derivative of sine x is cosine x. So that'll come into play as we use our product rule here. So I'm first going to do first times derivative of the second. So here is my first function times derivative of the second, plus the second function times derivative of the first. So here is my second function times derivative of x squared is 2x. There's not much you can do with this as far as simplifying, so this would be totally okay to present this as your final answer. If you were matching up multiple choice and you didn't see this answer, you might look and see between my two terms, they do have an x factor in common, so you might factor that x out. And it would look like this, but either one of these answers is fine. So just make sure whenever you have the product of two functions, there's my telltale sign, that multiplication symbol, I do the product rule. I cannot just do derivative of the first times derivative of the second. Not quite as friendly as limits were. As I look at number 4, I have a quotient. And just like with the product, it is not going to just be the derivative of the quotients. I've got to follow this thing that we call the quotient rule. And I've got it up here at the top, so we'll just go over this real quick. If you want to do the derivative of a quotient, f divided by g, it is the bottom function times derivative of the top. This is a subtraction. The top times derivative of the bottom, all over the bottom function squared. This function is not quite as friendly as the product rule because subtraction is not commutative, so you're not allowed to switch these guys around. And it's a little counterintuitive because it actually starts with this bottom function as is times derivative of the top. So you don't have to memorize this in this exact form, but just some version of it. So let's see what this looks like in action. And we'll just go ahead and write it down here by this problem so we have something to look at. And here it is off to the side. So the top is my f, the bottom is my g. So I'm going to start my y prime by doing the bottom function as is times derivative of the top. So here is my bottom times derivative of this, just power rule. Make sure when you do the derivative of that binomial on top that you encase it in parentheses, because when I go to simplify this, I'm going to have to distribute that x squared through the parentheses. So now I am to this point in my formula. So I've done this. So I'm to the minus top times derivative of the bottom. So this part here, the fg prime is this part right here. And my subtraction sign right here is the subtraction sign. And now I have to do all over the bottom function squared. And now all that's left is to do a little algebra and simplify this. So I'm going to distribute that x squared through the parentheses. And I'm also going to distribute this 2x and this negative through this parentheses. So I got the negative coming in from the left, and I've got the 2x coming in from the right. And just remember, when you multiply with the same base, we're adding these exponents. That's where the 6 comes from. But when you have a power to a power, I got this 4 by actually multiplying these 2's together. And I can simplify this a little bit by pulling my like terms together. So I'm going to combine those, and I'm going to combine those to get to my next step. And one more little algebra move. I can divide that x to the 4th into each term in the numerator to get this as my final answer. And I end up with 24x squared minus 4x. We have another quotient rule here on the back. Maybe stop the video and give this one a go, see how you do. So when I look at this, I see dy dx, so that means derivative of y with respect to x, and here's my y. I see I have a quotient here. I'm dividing, so that lets me know I'm going to use the quotient rule. Notice how when I did this, I kept these binomials in parentheses. The 2x and the 3 don't really matter, but the binomials in parentheses matter because my next step is going to be to distribute. So this is my derivative answer. All I have to do is a little algebra to clean it up a little bit. And that gets me to here. Just watch the signs. Make sure that this negative gets distributed from the left and that the 3 is coming in from the right. Also note that I didn't expand this binomial in the denominator. Just in general, things are more useful to you in their factored form in hopes of finding a common factor. So I'm just going to leave that guy alone. And all I have left to do is combine my x squared like terms in the numerator. And this is my final answer. As far as factoring this numerator, the only reason I'd want to factor it is to cancel a common factor in the denominator. And the only thing that would be a common factor is 3x minus 4, and I can see that's not going to be a factor up here. So even if it is factorable, I'm just not going to worry about it because I know it's not going to lead to a more simplified version of this expression. Our last group of examples has you using this product and quotient rule in conjunction with a table. So our information is given not as a function, but in tabular form as we have over here. So question 6 says r of x is f times g, so there's our product. I have to find r prime of 2. And my AP exam tip number 1 over here says don't rush just to find r prime of 2. Let's start by just finding that r prime of x function first. So my first move is just to find r prime of x. Generally, just showing this derivative is going to earn you a point. And if I want to find r prime of 2, now all I'm going to do is all of these x's are now going to become 2's. So now I'm just at a point where I'm going to pull my table values, and these are all evaluated at 2. So I'm going to make sure that I am looking at this 2 row to get my values. And this is my answer here. And it would be perfectly okay to present your answer like this. Nobody's going to require you to do calculations, but it's just 32 minus 2. So my r prime of 2 value is 30. And again, doing a problem like this is not just about that bottom line answer. If you have an answer with nothing else shown, it's worth nothing to you. So make sure you show the derivative, show these values as they appear in the table. So I want to see these values here and your final answer of 30. Question number 7, I'm finding j prime of 5, and I'm told g of x is f divided by g, and that is a quotient, so I'm going to use the quotient rule. And so I laid out my derivative, I have plugged in my 5, and now I'm ready to turn to the table to find my values. Whenever you're working with tables, it's always a good idea to show these values as they're coming from the table. So I want to show in my work the -6, the -1, the 1, and the 3. So show those values that are coming straight from the table. And as a final answer, this is actually okay. You can simplify if you want to, but if you do, you better make sure you do it right. And I get my j prime of 5 value is 17. And question 8 is tying together what we did in section 3, which was write the equation of a tangent line. So we know to write an equation of a tangent line, so here's our key phrase right here. I need a point and a slope. For my point, I know my x-coordinate is 5, and to find my y-coordinate, I just have to do j of 5. To find j of 5, I have to go back to how j was defined, and I see up here it's just f divided by g. So my j of 5 is just going to be f of 5 divided by g of 5. Looking up at my table, I can see that my f of 5 is a -6, and my g of 5 is a 1. So the y-coordinate for my point is going to be -6. My point is 5, -6. And for my slope, I have to do j prime of 5. Well, that was just my answer to number 7. So my j prime of 5 is just going to be 17. And using this as my point, 5, negative 6, and 17 as my slope, I'm going to use point slope and write my equation. And here we have our equation of a tangent line. So just to recap what we talked about, whenever you're doing the derivative of a product or a quotient, you have to follow the product or the quotient rule, whichever one is applicable. Make sure that you show all the work that you're doing. And don't forget, the simplifying is not mandatory. If it's multiple choice, you'll need to simplify as far as necessary to target the correct answer. But if you're on free response, you can just finish the calculus and be done. And make sure you have a firm hold on how to use these, because they will show up in a lot of what we're going to be doing in the future.